Okay, good morning. This is our 25th lecture. So, in the previous lecture, we started our discussion on effect of pressure on uh, isentropic flow through nozzle. Okay. So, this is something which we are actually trying to study. And you would be remembering that what we have done is basically, so if I plot pressure as function of the length along the nozzle. Okay, so here say this is my P by P naught, and say here if I plot my Mach number as function of x, then this particular location shown by green line is corresponding to A by A star is equal to 1. Okay, so here say this value is 1, and here say this is my Mach number equal to 1. Okay, so we had seen that for an isentropic flow through a nozzle, if at the throat I am able to achieve a Mach number of 1, corresponding to that my profile for Mach number will be something like this. So this is how my Mach number will look. So at the throat I will be having Mach number 1. Before the throat I will be having subsonic flow, and after the throat I will be having supersonic flow, and this profile of Mach number can be obtained from area Mach number relation. Okay, then second important point, we studied that this pressure decreases along the isentropic flow through a nozzle, and we find that at this particular point throat, this pressure has to be equal to 0.528 times. Okay, so P by P naught ratio will be 0.528 times. Fine. And ultimately, if I have a nozzle, so if I place the nozzle in the atmospheric conditions, flow will not automatically take place through the nozzle. So what we have to do for the flow to occur through a nozzle, we have to actually maintain the pressure difference between the uh, starting and the ending point of the nozzle. Okay, so if I have to achieve this type of Mach number profile and this type of pressure profile, so what I have to do, I have to, if my at inlet pressure ratio P by P naught is 1, at exit I have to say maintain this pressure ratio of P exit by P naught, and this pressure has to be exactly equal to this pressure. If it is deviating from this, then we will be finding some different situation. Okay, then second thing I have emphasized that, say if our pressure is not exactly equal to PE, if pressure is other than PE, then what will be happening? So for that situation, we had taken a nozzle, identical nozzle, and then we tried to plot the pressure as well as the Mach number. So say this is my P by P naught, it is starting from 1, and this graph I am plotting along the x, and then this is my once again along the x, and say this is Mach number over here, and this is corresponding to Mach number equal to 1. Okay, so here what we saw that if my inlet difference between inlet pressure and outlet pressure is very small, so say this is the throat point over here. So I said that if say this is my inlet pressure and say outlet pressure over here is some value PE1, and PE1 is very small in comparison to this one. So what I will be having, I will not be having very high flow rate within the nozzle. I will be having very small amount of mass flow of the fluid through the nozzle. So because of that, I will not be able to achieve Mach number equal to 1. Okay, so if I am not able to achieve the Mach number equal to 1, so inside my nozzle flow will throughout remain subsonic, and for the subsonic flow we know that in diverging section actually flow velocity or Mach number decreases. So here I will be having profile something like this. Fine. Then corresponding pressure profile, if you see, so initially we are having converging section. So in case of converging section, as velocity will increase, so pressure will keep on decreasing, reach a minima at the throat, and after this point, because the flow velocity is decreasing, so we will be having regain in the pressure, and then it will once again try to reach at this point. Okay, and if I now slightly decrease the pressure ratio, say if in place of PE1 if I take some pressure PE2, then ultimately my pressure profile will go something like this, and then Mach number will also try to lift up. Okay, and this process will keep on happening unless or until I am able to maintain this pressure. Okay, so I will find not this pressure, so this pressure is different and here something different will happen. So ultimately then what will happen, I will find some pressure, say this is my pressure PE3. I will find some pressure ratio, pressure difference PE3, P naught minus PE3 across the nozzle, such that what I am able to achieve, I am able to achieve a Mach number of 1 at the throat. But after throat, once again I have nothing but subsonic flow. Okay, so Mach number just reached equal to 1, and once again the flow has actually deaccelerated in despite of accelerating. Is this point clear? So here you have to make important point. Here whatever I am saying, the pressure required to achieve first subsonic and then supersonic flow situation, that pressure is PE. But pressure which is required to achieve Mach number at the throat equal to 1, but after that once again the subsonic situation, that pressure I am saying as PE3, and PE3 and PE are not same. Is this point clear? This is important point, okay, because based on this only we will be having our further discussion. Okay, so let me once again emphasize that what I am trying to say is, if you maintain a pressure difference across the nozzle P naught minus PE, where PE is the desired pressure at the exit as per the relation of isentropic subsonic flow up to the throat and then isentropic supersonic flow in the diverging section. Okay, so as per that relation, whatever pressure I am getting at the exit, that I am calling as PE. If across a nozzle I maintain P naught minus PE, then I will be able to achieve this curve and this type of Mach number relation. But if I maintain a pressure across the nozzle P naught minus PE3, what pressure difference? P naught minus PE3. In that case, I will be having initially isentropic subsonic solution. Okay, and after this point also we will be having isentropic subsonic solution only. Is this point clear? Point is clear? So here I have isentropic subsonic, here also I have isentropic subsonic. Okay, so it means that PE3 and PE are completely different. Okay, another important point is that for subsonic case, if you maintain different exit pressures such as PE1, PE2, PE3 or PE4 etc. So if you achieve different exit pressures, we will be finding that we will be having different isentropic subsonic solutions possible. Okay, so it means that for the flow through a nozzle there are multiple isentropic subsonic flow solutions possible. But supersonic flow situation will only happen if my pressure is being maintained equal to PE. So corresponding to supersonic situation, I have only a unique isentropic supersonic flow possible. Is this point clear? Okay, what is the issue? Okay, it has come. So I will be having unique isentropic flow solution particularly for the supersonic condition, whereas in case of subsonic I can have multiple. Okay, one another important point, once I have reached to pressure PE3, so pressure PE3 is the one which is maintaining Mach number equal to 1 at the throat. So if I go below, so say if I go to some pressure PE4 which is less than PE3, then also what I will be finding? I will be finding that I am not having any further change in the mass flow rate, and ultimately I am able to achieve this curve, same curve for Mach number. So at the throat I am only able to reach Mach number equal to 1. Because why? Because from our very initial relation, area velocity relation, whatever I have derived, dA by A equal to m square minus 1 into dV by V. From that relation, it is constrained mathematically that Mach number, that area of the variable cross section will be minimum corresponding to Mach number equal to 1 only. So this is a physical constraint we have. Okay. So even if you decrease the pressure less than PE3, then also I will be finding that my mass flow rate of the fluid will not change, because from the area velocity relation for an isentropic situation, corresponding to minimum area, Mach number has to be only equal to 1. Is this point clear? So that is the reason we say that in case of nozzle we are having choked flow situation. So once we reach this pressure difference PO minus PE3, our flow has actually choked. Because why? Because if I maintain any pressure difference PEO minus PE4, which is less than PO minus PE3, then also my mass flow rate, if say I have ME3, M dot E3 corresponding to this, so here also mass flow rate will remain M dot E3. Why? Because at the throat, Mach number has to be equal to 1 only. Is this point clear? So this gives us very important conclusion. So the conclusion is that if I plot mass flow rate m dot through the nozzle as function of pressure, so I can say that if say this is my PO, so PO is pressure of the reservoir, or I can say pressure at the inlet of the nozzle. So PO is the pressure. So if my pressure is at exit, say this is the pressure at exit, PE1. So when I have PO minus PE1 pressure difference, corresponding to this I will get some mass flow rate over here. Say this is the mass flow rate I am getting. Okay. When I go to another pressure PE2, exit pressure PE2, then I will be having some higher mass flow rate. Okay. When I go to pressure PE3, then I will be having slightly more higher mass flow rate. So this is corresponding to PE3. But when I go below PE3 to any pressure, if I go, mass flow rate will remain fixed. Okay. So I will get this type of curve for the mass flow rate. Is this one clear? Point is clear? So what I have said is that corresponding to PE1, PE2, our mass flow rate has increased. But when I reach the situation that at the throat, Mach number has become unity, corresponding to that point, whatever mass flow rate is there, that is not changing. And after this, I have horizontal mass flow rate for all the decreased values of the pressure. Okay. One important point is that we saw that corresponding to Mach number equal to 1, at the throat, our pressure ratio P by P naught is nothing but equal to 0.528. So somewhere over here I will be having pressure 0.528 times of P naught. Okay, but this entire is nothing but the choked flow situation. So this horizontal portion is choked flow situation. Okay, and you will be surprised to know that if you are having only the inlet portion, converging portion of the nozzle, and then throat. Okay, if you remove the diverging portion from the nozzle, then you must maintain this much pressure difference in order to have Mach number equal to 1 at the throat. But once you put diverging section also along with the nozzle, so what happens? Diverging section leads to some pressure recovery. So because of that, now whatever the pressure difference you have to maintain, that is actually even less. Is this point clear? So what I said is that if you only consider your converging section and throat and remove the diverging section, and then you want to achieve a Mach number of 1 at the throat, then you have to maintain this pressure difference of P naught minus 0.528 times of P naught in order to reach a Mach number of 1 at the throat. But when we put the diverging section, ultimately for subsonic flow situation, diverging section leads to nothing but pressure recovery. Okay, so because of that, because of this pressure recovery, even now, along with the diverging section, the pressure difference required between the inlet and outlet of the nozzle is P naught minus PE3, which is less than even this pressure difference. Okay, this point is clear. Now now let's try to see that what will happen in the downstream. Okay, so till now I said that in the inlet portion, means up to the throat, flow situation will remain the same. Okay, up to the throat, flow situation will remain the same even if you keep on decreasing the pressure. But what will happen after the throat? Because after the throat, we also know one important point. We know one important point is that if we are able to achieve pressure exactly equal to that of whatever we have obtained from area Mach number relation, then only I will be able to achieve the isentropic supersonic flow in the diverging section. If pressure is other than that, then what will happen in the diverging section? That is actually very interesting to know. Okay, so let's see that portion. So up to this point, do you have any difficulty? Because if there is confusion at this stage, then next portion will not be clear. It is fine? Okay. Okay, so what I will do now over here, I will try to superimpose the profiles, which will give actually very interesting finding. Say this is my Mach number versus X, this is my P by P naught versus X, and this is the point of minimum area where I have A by A star equal to 1. Okay. This is the point corresponding to Mach number equal to 1, and this is the point corresponding to P by P naught is 1. Fine. So now this is very clear that if I maintain pressure equal to PE3, if I maintain pressure equal to PE3, what will happen? I will be having first increase of Mach number up to 1, and then I will be having decrease of Mach number, because pressure equal to PE3 is corresponding to the complete subsonic isentropic flow through the nozzle. Okay, so here I will be having increase of Mach number, and then I will be having some decrease of Mach number. So this is something which I will get corresponding. So this line I can say is, this line is nothing but isentropic subsonic line. Is this point clear? This line is isentropic subsonic line. Now if I consider that I am able to maintain a pressure of equal to PE. Sorry, let me first draw the pressure profile for this. So pressure profile for this will be, so this is my PE3. Fine. P3 by P naught, let me write. Now another important point is, if I am able to maintain the pressure equal to PE, what is PE pressure? Exit pressure for isentropic subsonic supersonic situation. Okay, so if you see my first slide, so PE is which maintains isentropic subsonic super. Let me give subscript to this. Let me call it PE0. If it is creating confusion with the PE exit pressure, so let me call it as PE0. Okay, so what is PE0? PE0 is the pressure which can give us isentropic subsonic and isentropic supersonic both. So it means if I maintain P 0, then I will be able to replicate these two curves. Okay. So what I will get then, up to this point it is the same, and after this point also my Mach number will keep on increasing. So this is the for isentropic up to this subsonic, but after this isentropic supersonic. What will the pressure profile for this? So this will be the pressure profile for this. Here I will be having P E 0. Fine. And corresponding to this point I will be having 0.528. So this is the pressure profile for this. Is it okay? Sorry, I have drawn it wrongly. So basically up to Mach number of 1 it should superimpose with the previous profile, because flow is remaining the so up to this it will be superimposing, and then it will keep on actually going like this. So this point is my actually 0.528. Okay. Any issue up to this point? So now interesting thing comes in this zone. If you maintain pressure P3, then you are able to find this thing. If you maintain pressure P0, then you are able to see this thing. So same is reflected in Mach number and this. So basically if you see in both cases, up to the throat nothing is happening, but after the throat changes are happening. Okay. Now interesting point is that what will happen if my pressure is in between these two values? In between. So if I have any exit pressure in between PE0 and PE3. That is interesting point to observe. Okay. So say I have any pressure that is PE4 and it is greater than PE0 and less than PE3. What I said, I have now pressure PE4. So my new pressure point is say somewhere over here. This is my new pressure point. So this point is PE4. Now how to achieve this PE4? Because if you go to PE3, then your line will be like this. If you go to PE0, then your line will be like this. And up to the throat nothing will change. So things has to change after the throat. So after the throat, flow has become isentropic. Supersonic. So as flow has become supersonic, it must end at this point. But if my pressure is P4, which is greater than P0, so it cannot exit at this point. So what we will be finding, because exit must reach to this pressure, so it means that if I am following this line, somewhere over here I must have a jump of pressure and then I should reach to this point. Is that clear? So ultimately, if I am following a supersonic line, at some point of time, there should be a jump of pressure which is able to maintain a pressure PE4 which is maintained at the exit of the nozzle. Is this one clear? So corresponding to, so if I have this type of jump of pressure, that will be only possible if I have presence of a shock wave. So ultimately what happens, if I maintain any pressure in between P3 and P0 at the exit, I have the presence of a normal shock wave. So here I will be having presence of a normal shock wave. So what this normal shock wave will do, so just above the normal shock wave, my flow over here was supersonic. So here flow was supersonic. So this supersonic curve was coming and then it has experienced a shock wave. When it experienced a shock wave, suddenly there is increase of pressure. Increase of pressure, and this increase of pressure will also do one thing. This will decrease the Mach number, because always behind the shock wave I have a subsonic flow. So now from this point my pressure curve will follow the subsonic process. So in case of subsonic process, I have recovery of the pressure, so there is increase of pressure. And important point is that in my Mach number I will be finding a decay. Okay, so there will be decay in the Mach number, and then it will follow subsonic situation, something like this, and this will be my exit Mach number. Is this situation clear? This is important to understand actually. Do I need to repeat, or is it clear? Okay, so important point is, if I have any pressure in between P3, P3 is the pressure required to achieve sonic condition at the throat for complete isentropic subsonic flow, and P naught is the pressure which gives us combined isentropic subsonic and isentropic supersonic situation. So if my pressure is in between these two, then what I have to do, I will be finding that in the converging section flow will be choked, but in the diverging section I will be finding the presence of a normal shock wave. Okay, and that normal shock wave will lead to the pressure equalization, so that the downstream pressure condition can be reached, whatever is applied. Okay, is this point clear? So it means that if you do not precisely control the pressure inside the nozzle, there can be presence of a normal shock wave. Okay, now important point is that what will be the location of this normal shock wave? Okay, at which point this normal shock wave will form. So location of the normal shock wave is something which is controlled by the value of the exit pressure. Okay, so depending upon the value of the exit pressure, actually how much back pressure we are supplying from the end, so depending upon that, actually this the location of the shock wave actually shifts. Okay, so I can say that let me is this point clear, or do I need to redraw this diagram? Is it clear? Okay, if it is clear, then it's fine. Okay, so important point now, what we have to do, we have to see that how to control the location of the normal shock wave. Okay, so the point is just ahead of the normal shock wave I will be having some pressure. Say this is my point 1, this is my point 2. In the upstream and downstream of the shock wave. So in the upstream of the shock wave I will be having some pressure P1. In the downstream of the shock wave I will be having some pressure P2, and then from P2 to PE I will be having some pressure recovery. So the sum of pressure recovery and P2 should create a situation that they are giving pressure on the upstream of the shock wave as P1. So basically it's the combination of the pressure on the downstream of the shock wave and whatever the portion we are having left with where pressure recovery will be taking place, because these two things are controlling that how to reach at P4. Okay, so depending upon that the presence of the actually shock wave is controlled. And if I keep on decreasing this, say from this point if I come over here P5, P6, then my shock wave will keep on shifting towards the exit side. Okay, so important point is, if I go here at some point PE5, which is less than PE4, now recovery has to be this much only, so shock wave will occur somewhere over here. If I further keep shifting down, then shock wave will occur somewhere over here. So next point is that so PE4 was the situation corresponding to occurrence of normal shock wave over here. So if I decrease the pressure to PE5, which is less than PE4, then I will be finding that shock wave will move moves toward exit. If I further decrease pressure PE6, which is less than PE5, then it will further move toward exit. Is this point clear? So what I am trying to say is that so I may have a situation where my pressure has decreased and then just reached some very small value, and then there is sudden increase at the exit and then reaching to some value. So here say this value is P5 by P0, and this value just upstream is PE6 by P0. So here what I will be finding, the shock wave will occur somewhere over here, just at the exit. If you have to have a supersonic nozzle, then this shock wave is also not good, because what it will be doing, it will be ultimately decreasing the Mach number at the exit. But you want a supersonic Mach number. Okay, so is this point clear? So now say, let's assume that this PE6 whatever we are having, that is nearly equal to PE0. That is something which is happening over here. So PE6 is almost nearly equal to PE0. Okay, which is the pressure required to maintain, supersonic, complete supersonic, isentropic supersonic situation at the exit. Okay, then I will be finding that I have a shock wave exactly near the interface. Now I can have two more situations within the nozzle. One situation I can have is that, say the pressure which is just at the exit of the nozzle is PB. So PB is I am calling as back pressure which is acting on the exit of the nozzle. So if there can be two situations, one situation is that this pressure point PE6, in one case it can be greater than back pressure PB, and in another case it can be less than back pressure PB. Point is clear? So what I am saying is PE6 is nearly equal to PE0, but say outside, just at the exit of the nozzle, I have back pressure is PB. Now, one situation is just at the exit, my flow pressure can be slightly greater than the back pressure PB, and in another case it can be less than the back pressure PB. So what will happen to these two situations? That let's try to see. Here say PE6 is less than PB. Okay. So somewhere over here you will be having pressure PE6, and somewhere just outside your pressure will be PB. So here PE6 just at the exit of the nozzle is less in comparison to back pressure PB. So what will happen? I will be finding that at the corner of the nozzle there will be formation of an oblique shock wave, and this oblique shock wave, here what will be happening, this oblique shock wave will try to create this small pressure recovery over here. Okay, so this oblique shock wave will lead to pressure recovery. and here I will be having flow streamline, something like this. Okay, so this type of situation where my pressure within the nozzle exit is going below the required back pressure which need to maintain the supersonic situation, that type of condition is called as over expansion in the nozzle. We have over expanded the flow so that its pressure has gone below the desired back pressure which is needed to maintain the flow. Okay, then another situation can be if my PE6 is greater than PB. So in this type of situation, what happens? Say if you are not able to precisely control the pressure at the nozzle exit, and if it is slightly greater than back pressure, then I will be finding here, I will be having formation of series of Mach waves. So what Mach waves does? These also lead to decrease in the pressure of the wave. So here I will be finding that through these Mach waves, I will be having actually further expansion of the flow, and here pressure will be PB and here pressure will be PE6. So in this case, my required back pressure was PB, but pressure at the exit of the nozzle was PE6, which was greater than PB. So here I have nothing but situation of under expansion in the nozzle. Is this one clear? This is important to understand. Okay, so basically many times it becomes challenging to precisely control the pressure. There is some issue with the connector. Let me fix it. Yeah, it is fine now. Okay, so many times it is not precisely, we are not able to precisely control the pressure. So in case my pressure at the exit is slightly less than the desired pressure, then I will be having formation of these oblique shock waves which will maintain the desired pressure. And here I will be having, if pressure is greater, I have an under expansion situation, then I will be having formation of Mach waves which will actually maintain the pressure. Is this one clear? Now let's try to see, because we have seen very important aspects, and let's try to see now how we have to proceed for numerical problems. If we have to solve the numerical problems based on this, then how we can do that. Okay, so I will try to take up two questions quickly over here, and then we will discuss one more important aspect. So this is my numerical problem 1. Here it is given that exit to throat area ratio is 2 for a nozzle, and initial pressure is given as 1 atmospheric and exit pressure is given as 0.95 atmospheric, and you are given a task to calculate Mach number at the throat and Mach number at the exit of the nozzle. So question is clear? You are having a nozzle. So for nozzle we know that this is our AT throat area, this is our AE exit area. So exit area by throat area ratio is given 2, then P naught pressure at the starting is given 1 atmospheric, P exit pressure at the exit is given as 0.95 atm, and you are supposed to calculate Mach number at the throat and Mach number at the exit. So how to proceed for the solution of this? Can you tell me? We have to first identify whether we will be having isentropic subsonic supersonic situation, or we will be having complete isentropic subsonic situation, or we can have isentropic subsonic, isentropic supersonic, and a normal shock wave. So which out of these three situations we will be having, that first we have to identify. So for identifying that, what we have to do? We have to determine pressures PE3 and PE0. PE0 is the pressure which is required to maintain isentropic, subsonic, supersonic, and PE3 is which is giving purely subsonic. Okay, so let's first try to find out the pressure ratio. So for finding out pressure ratio, actually what we have one important relation: A by A star square equal to 1 by Mach number square 2 by gamma plus 1 1 plus gamma minus 1 by 2 Mach number square whole power gamma plus 1 by gamma minus 1. Okay, so from this relation, A by A star is AE by AT. So AT basically we consider corresponding to A star. Okay, for isentropic, subsonic, supersonic flow condition. So for this is important, for isentropic, subsonic, supersonic flow, exactly the ideal condition. A star is equal to AT. Area at the throat is equal to A star, because at that A star is where we get sonic Mach number, and AT is area of the throat. So if we have this type of ideal situation, then at throat only we will get the sonic condition. So A star equal to AT. So here if I put this condition, so it is given AE by A star is given. So if I put AE by A star, I will be able to find out the Mach number at the exit. Is this point clear? So from this relation I will get Mach number at the exit for supersonic flow situation. So this Mach number will be nothing but supersonic Mach number. Is this point clear? Now I can put this value of supersonic Mach number into the stagnation pressure relation, and I can determine the pressure ratio. Okay, so if you recall from the previous lecture, we have derived pressure ratio PE by P0 as 1 plus gamma minus 1 by 2 m square, sorry, let me write this as PO by PE, ME square. So this will be Mach number at the exit square whole power gamma by gamma minus. So if you calculate this pressure ratio, it comes out to be 10.69. So your pressure ratio is 10.69. It means that exit pressure has to be P0 by 10.69. So P0 is 1 ATM divided by 10.69. So which is coming out to be 0.0935 ATM. And what is your given pressure? So it is less than point. It means that I will not be having the formation of a, I am not having actually supersonic flow in the diverging section. So if I don't have supersonic flow in the diverging section, it means my Mach number at the throat is not equal to 1. If Mach number at the throat is not equal to 1, it means AT is not equal to. Is this point clear? Important to understand. You have to make analogy. So what I said is that we are not able to achieve the supersonic flow at the exit. If we are not able to achieve the supersonic flow at the exit, it means Mach number at the throat is not equal to 1. If Mach number at the throat is not equal to 1, then AT will not be equal to A star. Okay. So now we have to find what will be AT. So how to find AT? So we are having the given pressure ratio. So if you see over here, pressure ratio, given pressure ratio is P0 by PE, which is 1 by 0.95, and it is 1.053. Is this point clear? Now this pressure ratio I can equate to 1 plus gamma minus 1 by 2 m square, and this gamma by gamma minus 1. Okay, from here if I calculate the value of Mach number at exit, it comes out to be 0.28. So as Mach number at the exit is coming out to be 0.28, it means that, meaning is clear that we are having purely subsonic flow situation. Okay, now what we have to do? Now if my Mach number at the exit is known, can I apply area velocity relation over here? Because area Mach number relation. So area Mach number relation gives us two branches, supersonic as well as subsonic. So this is applicable for both. So now I can apply here area. I will not write the full expression again. So I can apply area Mach number relation. From this area Mach number relation, what I will be getting? Mach number is known to me. I will get the ratio of exit area divided by A star. So AE by A star, from here if I calculate, that comes out to be 2.17. So AE by A star is coming out to be 2.17. But in your question it is given that AE by A throat is equal to 2. So it means that AE is same in both expressions. This ratio is 2.17, this ratio is 2. So it means that area of throat is greater than A star. Area at the throat is greater than A star. So now what we have to calculate? We have to calculate, because we want to calculate the Mach number at the throat. So we have to calculate for the throat, that I can calculate from area Mach number relation. But area Mach number relation I can only apply if I have ratio of area of that particular section where I want to calculate the Mach number divided by A star. Okay, so it means that I need to, if I have to calculate Mach number at the throat, then I must determine the ratio of AT by A star. Is this point clear? So I have to calculate AT by A star. So what I will do, I will now take the help of area given at the exit. So I will do AT by A exit into A exit by A star. So A is cancelling, so equation is remaining unaffected. Now AT by AE by AT is given 2. So this first ratio will be 1 by 2, and AE by A star just now we have calculated. So that is 2.17. This comes out to be 1.085. Now what I can do? Now once again I have to apply this A by A star with Mach number relation for subsonic situation, and I will get Mach number at the throat is 0.72. Okay, so it means that if you plot the Mach number relation, Mach number versus X is giving you curve something like this. 0.72, then it is decreasing, and then finally becoming 0.28 at the exit. So this situation is a purely subsonic situation. Okay, is this one clear? Shall I move to next question? You have to understand, while you will be doing the questions, you have to carefully do this. Okay, you will be having so many things to actually check and verify. That is why this topic is very, very important. Now whenever I will do the second problem, after doing second problem we will get one more important question that once again we have to answer. Okay, so let's see. Problem number 2 is, I have area at exit by area at throat equal to 3, and area at, okay, so equal to 2, I have to determine P exit by P naught. So in this question it is given that I have the presence of a normal shock wave, and normal shock wave is forming at location where A by AT ratio is 2. And you have to determine the ratio of PE by P naught. So question is, let me schematically also explain. Question is something like this. This is your AE, area at exit. This is your area at throat, and then it is given the question that I have somewhere the presence of a normal shock wave. Okay, and where this normal shock wave is forming, corresponding to that my area is A. So A by AT ratio is 2 and AE by AT ratio is 3, and you are given a task to calculate PE by P naught. Fine. Is it okay? Now let me give the condition on the upstream of shock wave as 1 and on the downstream of shock wave as 2. Shall we start for the solution? Okay. Okay, so first important point is, when we use A by A star relation, A by A star relation is applicable for isentropic flow situation. Okay. When I have the presence of a normal shock wave, we know that on the upstream and downstream of normal shock wave, flow properties are significantly different. It means that the region of the shock wave is actually non-isentropic. So I have one isentropic situation above the shock wave and then another isentropic situation downstream of the shock wave. But at the shock wave I don't have the isentropic conditions. Is this point clear? So before this also flow is isentropic and after this also flow is isentropic, but this is the portion where flow is not isentropic. So it means that if I have stagnation pressure P naught over here and if I have some stagnation pressure P naught 1 over here, so P naught will be equal to P naught 1 because this flow is isentropic. Up to this point there is no change in entropy. So if there is no change in entropy, there is no change in the stagnation pressure. Similarly, if I have P naught 2 as the stagnation pressure at point 2 and POE as the stagnation pressure at point E, so POE will also be equal to P naught 2 because in this portion also our conditions are isentropic. But across the shock wave we are having increase of entropy. So that's why P naught 1 will not be equal to P naught 2. Point is clear? This is important to understand at the starting itself. When we use, now another important point is when we use this A by A star relation with Mach number. A by A star relation with Mach number is applicable for isentropic flow situation. It is not applicable for non-isentropic because our assumption from the starting itself to derive area velocity relation was isentropic. So that is the reason that this A star value will not be same on upstream and downstream of the Mach number of the shock wave. Okay, so I will be having some different A1 star in the upstream side and I will be having some different A2 star in the downstream side, because this relation on downstream I have to separately apply and in the upstream I have to separately apply. So A1 star at the upstream will be different and A2 star at the downstream will be different. Is this point clear? So all of you are agreeing on this. Now important point is, if I have subsonic supersonic flow condition, then only normal shock will occur. Okay, so normal shock wave will only happen if after the throat I have a supersonic flow situation. So it means that corresponding to throat only I will be having Mach number equal to 1. So A1 star will always be equal to AT. A1 star will always be equal to area at the throat if our normal shock wave is occurring in the flow. Is this point clear? What I am saying is important actually. So that's why you people should listen it carefully. Okay. What I am saying is that normal shock wave will only occur when our flow is supersonic over here, and flow will be supersonic over here only if Mach number at the throat is 1, and corresponding to Mach number equal to 1 we define the star condition. So it means if a normal shock wave is present, always my A1 star will be equal to 80. Fine. And A2 star has to be different because A2 star is after the shock wave. Okay, up to this point it is clear. Now let's target the problem. So these are some important points. Now we can actually target the problem. So problem, if we solve, so first point is given that A by, okay, so let me consider, as I have defined, that upstream of shock wave is 1 and downstream of shock wave is 2. So I can say that upstream area of shock wave is A1 and downstream area of shock wave is A2. Is this point clear? So now if I write over here that A1 by A1 star, that will be equal to A by 80. Is this point clear? Because A1 star is equal to 80, and as shock wave is very thin, so just upstream of the shock wave is nothing but the location of the shock wave. So it means A1 is equal to A, because A is the location at which shock wave is forming. So this will be equal to A by 80, so which is equal to 2. Now what I can do, can I apply area Mach number relation? Because I know A1 by A1 star. So if I apply area Mach number relation, then Mach number at point 1 I can calculate from that relation, and this Mach number I have to choose for a supersonic one, because this relation gives us two solutions, one for supersonic, other for subsonic. So here we must choose the supersonic one. So supersonic one I will get Mach number using that relation as 2.2. So this, please you try the numerical calculations at your home, at your hostel. So what I am doing, actually I am trying to give direct numbers. Formula also you have to apply over here. So M1 will be 2.2. Okay. Now I know that if I have presence of a normal shock wave, I can predict the Mach number on the downstream. So for normal shock wave, M2 square is equal to 1 plus gamma minus 1 by 2 M1 square divided by gamma M1 square minus gamma minus 1 by 2. Okay, so this is the relation between M2 and M1. M1 I am knowing for a normal shock wave. So M2 from here comes out to be 0.5471. Is this point clear? Now we also know the relationship for P01 by P02 by P01. What is P02? Pressure, stagnation pressure on the downstream of the normal shock wave, and this is on the upstream of the shock wave. So we do have formulas available from the normal shock wave relations, and this ratio, if I calculate, this comes out to be 0.6281. Okay, this comes out to be 0.6281. Now if I use this relation M2, if I use this value M2 equal to 0.5471, and this is now on the downstream of the shock wave. Okay, so now if I apply area velocity relation, so from area velocity relation I can calculate the value of A2 by A2 star. So from here the value of A2 by A2 star comes out to be 1.27. Is this point clear? A2 by A2 star is coming out to be 1.27. Okay. Now important point is that, so once again whatever thing I explained, once again I am coming back to that. So I told that on the upstream of the shock wave area is A1, on the downstream of the shock wave area is A2, and we also know that the thickness of the shock wave is very small. So thickness of the shock wave is of the order of 10 to power minus 5 centimeter, very, very small. So as thickness of the shock wave is small, then A1 will be nearly equal to A2. So A1 will be nearly equal to A2. But if you see, A1 by A1 star is coming out to be 2 and A2 by A2 star is coming out to be, but A1 and A2 are nearly the same. So it means that A1 star has to be different than A2 star. This earlier also I told you, and now mathematically also I am able to prove that. Fine. Is this one clear? So it means A2 star will be something different. But what will be its value? That is something which we have to calculate. Okay. I know A1 star. Why? Because A1 star will always be equal to AT. If a normal shock wave is present, then A1 star will always be equal to AT. So I know A1 star, but A2 star I don't know. Okay. So it means that the portion of the the portion of the nozzle on the downstream of shock wave is having different value of, so that is I am defining as A2 star. So it means that if I have to apply area velocity relation to calculate Mach number at the exit, I must calculate ratio AE by A2 star. Is this one clear? Because exit point is on the downstream of the shock wave. So as it is on the downstream of the shock wave, if I have to apply area velocity relation, I must go to the downstream point. Okay. So that is the reason that I want now to calculate AE by A2 star. Fine. So how I will do? I will attempt it. So what I will do first, I will divide it by A2. So AE by A2 into A2 by A2 star. Okay, so I have multiplied and divided by A2. Then what I will do, I will also divide and multiply with throat area. So I have done AE by AT into AT by A2 into A2 by A2 star. Now can you tell me what is AE by AT? AE by AT is given in the question, which is 3. What is AT by A2? A2 is nothing but just downstream of the shock wave. So it will be equal to location of the shock wave. So that ratio of location of the shock wave area divided by AT is given as 2. So AT by A2 will be 1 by 2. Is this point clear? How it is 1 by 2? And then I have the third point, which is A2 by A2 star. And A2 by A2 star just now I have calculated in the previous slide, and it was how much? 1.27. So if I do this, I get over here the value as 1.905. So if I have this value, I can calculate now Mach number. Okay, so how? Now I will be using A by A2 star relation with Mach number, and then from this relation I get exit Mach number equal to 0.32. Now I have to choose which solution. This will give me two solutions, supersonic, subsonic. This is on the downstream of the shock wave. So I have to choose the subsonic solution because flow on the downstream of the shock wave will be subsonic. So I have to choose over here the subsonic solution. Okay. Then after this it is very simple. Now I can calculate stagnation pressure at exit by P exit by using 1 plus gamma minus 1 by 2 Mach number at exit ka square by gamma minus 1, power gamma by gamma minus 1. Okay, so this comes out to be 1.074. This comes out to be 1.074. So now if this is known, then I can do manipulations with pressure ratio and I can calculate my final parameter P exit by P inlet. So this I have to calculate. So this will be P exit by PO exit into PO exit by PO2 into PO2 by PO1 into PO1 by P1. Sorry, P naught. Fine. What I have done basically, I have taken the help of all the pressures which are actually known at the inner conditions. So what is PE by POE? We have just now calculated 1 upon 1.074. What is POE by PO2? POE is stagnation pressure at exit. PO2 is stagnation pressure just at the downstream of the shock wave. So these will be equal because this is isentropic flow situation. So 1 multiplied by PO2 by PO1 for a normal shock wave I have calculated. So that was coming out to be 6281. Okay, and then after this PO1 by PO0 is once again 1. So you will be able to calculate the pressure ratio of 0.585. Is this point clear? Okay. Now, so is this problem clear to all? Now in this problem, it is important to mention that in this question, it is given that the normal shock wave is occurring at A by AT equal to 2. But in reality, what challenge you will be facing? In reality, challenge is that we will be only knowing the upstream and the downstream pressure, but we will not able to, this data will not be known to us that where shock wave is occurring. So it means that the major problem is that we can apply this whole analysis, but before analyzing this analysis, we must also be able to predict the location of the shock wave. So how to do that? Earlier I thought that I will be able to do it today only, but now I will try to take up that in the next lecture. Okay.